Welcome to This Explainer. Today, we're going to decode the universe's ultimate HR department, physics. You see, just like a strictly managed office, the universe has a very specific set of rules for how absolutely everything, from a tiny pebble to a massive planet, is allowed to behave. And today, we're cracking open that rulebook to figure out exactly what causes things to move, stop, or completely change direction.
Let's just dive right into it, because honestly, squeezing a lemon is kind of the perfect way to see how the universe bosses objects around with its invisible hands. Think about it. When you squeeze that lemon to make lemonade, you're fundamentally altering its shape, right? Or a ball sitting quietly on the grass only starts moving when you actually kick it. All of these everyday actions require something fundamental to happen. They require a physical cause.
So, Section 1, meet the boss, force.
These bossy, invisible pushes and pulls? We call them forces, and they always have a specific strength or magnitude and a specific direction. We actually measure this cosmic bossiness in newtons, written with a capital N in honor of the physicist who figured a lot of this out for us. You know when you measure weight using a spring scale? Well, weight is actually just the gravitational force with which the Earth is pulling down on an object. So when you pull on a spring balance, it's measuring the exact force in newtons with which you're pulling.
Now, consider this hilariously tiny number, the Youngton Newton. No, I didn't make that up. It's a completely real measurement scientists use in specialized experiments for incredibly minuscule forces. To give you some context here, a super light touch on your arm is about a millinewton, or 10 to the negative 3 newtons. A Youngton Newton is 10 to the negative 24 newtons. It's just wild, and it really shows you just how unbelievably sensitive the universe's rulebook can be.
Moving on to Section 2, the ultimate tug of war. Balanced and unbalanced forces.
Because here's the thing, forces rarely act alone. They are almost always locked in this stubborn cosmic tug of war. Whenever you try to push a really heavy piece of furniture across the floor, you've definitely noticed that it fights back. The force of your hand pushing forward is instantly battled by the invisible, sticky force of friction, perfectly balancing you out in the exact opposite direction. If you push gently, friction just matches you. The forces are balanced, meaning the net force is zero, and absolutely nothing happens. The heavy object just sits there, mocking you.
That box is only going to budge when your push creates an unbalanced force. You literally have to push hard enough that your force becomes larger than the maximum force of friction. When that finally happens, you create a non-zero net force in the forward direction. It's only this unbalanced net force that finally forces the object to change its state and actually start moving.
Which brings us perfectly to Section 3, Law 1, the couch potato.
This first law basically says that all objects possess intense couch potato energy, a tendency scientists call inertia. But honestly, before Newton locked this down, Galileo Galilei was actually pondering this exact concept back in the 17th century. Finding a truly frictionless surface to test this on back then was way too much work. I mean, practically impossible. So Galileo cheekily just imagined it in his head. He argued through thought experiments that if a body moved along a perfectly horizontal, smooth plane with zero impediments, it would just continue to move indefinitely, forever.
So the crucial takeaway here is that objects just want to keep doing exactly what they're already doing. An object at rest remains completely at rest, and an object moving at a constant velocity, meaning in a straight line at the exact same speed, will just keep doing that forever. Well, unless a net force steps in and rudely interrupts it. You don't need a continuous force to keep something moving in a frictionless void. You only ever need a force to change what it's already doing.
All right, Section 4, Law 2, the heavyweight hustle.
Please welcome the absolute reigning heavyweight champion of physics equations. Force equals mass times acceleration. Good old F equals ma. This is Newton's second law. It tells us that the magnitude of an object's acceleration is directly proportional to the net force applied and inversely proportional to the object's mass. In everyday terms, push harder, it goes faster. Make it heavier, it's way harder to speed up.
Think about it like this. Imagine pushing a super heavy box and then kicking a light soccer ball with the exact same amount of effort. The results are totally different, right? The lighter object, the soccer ball, will experience a massive acceleration and speed up incredibly fast. The heavy box, having a much larger mass, is going to barely budge with that exact same force. Mass is quite literally a measure of how stubborn an object is against changing its motion.
And this whole mass and acceleration math is exactly why a cricketer instinctively pulls their hands backward when catching a really fast-moving ball. The ball has mass, and it is coming in hot. By pulling their hands back, the fielder increases the time it takes for the ball's high velocity to drop to zero. Increasing the time reduces the acceleration, and since force equals mass times acceleration, reducing the acceleration drastically reduces the painful force hitting their hands. It is quite literally self-preservation through physics.
And finally, Section 5, Law 3, the universe claps back.
This law is basically the universe's ultimate rule of karmic retribution. Forces always come in pairs. For every single action you take, the universe, hilariously and instantly, pushes right back. When someone climbs a tree, their legs push down against the trunk, and the friction from the trunk pushes the person equally upwards. When you walk, your foot pushes the ground backwards, and the ground pushes you forward. When a gun fires a bullet forward, the exact same amount of force throws the gun backward into the shooter's shoulder.
This perfectly explains why forcefully shoving water backward with a paddle somehow magically teleports your canoe forward. You are exerting a force on the water backward. According to Newton's third law, the water has absolutely no choice but to exert an equal force on your paddle in the forward direction. It's really important to note here that these two forces act on two entirely different objects. You push the water pushes you.
So I want to leave you with this final thought to ponder. If gravity pulls an apple down to the earth, Newton's third law says the apple is pulling the earth up with the exact same amount of gravitational force. So why on earth don't we see the planet rocketing up to meet the fruit? Well, because of F equals ma. They pull each other with equal force, but because the Earth is so impossibly, unimaginably massive, its acceleration from that tiny force is practically zero, leaving you with a delicious snack, a perfectly stationary planet, and hopefully a newfound appreciation for the universe's invisible rulebook. See you next time.